Is Occam's razor still the gold standard? From the bias-variance trade-off to modern data science and machine learning. For centuries, scientific inquiry has been guided by the principle of parsimony, commonly associated with Occam's razor. Within statistics and predictive modeling, this principle contributed to a preference for simpler models that can generalize well to new data. Classical statistical thinking therefore emphasized limiting unnecessary variables, reducing redundancy, and controlling overfitting through carefully constrained model specifications. Under the traditional bias-variance framework, excessive model complexity was considered risky because highly flexible models could fit noise rather than discover meaningful structure. Consequently, generations of researchers were trained to balance explanatory or predictive performance against simplicity. To support this goal, statisticians developed numerous variable selection procedures, including forward selection and backward elimination in stepwise regression, the maximum R-squared method, and Mallow's CP. A humorous example illustrates why an excessively complicated model can become practically useless even when it appears statistically impressive, such as when it produces a very high R-squared. A student once asked a professor which factors were related to academic performance. Put simply, the student wanted actionable advice on how to improve his grades. The professor proudly replied that a 50-variable regression model could predict nearly 100% of the variation in student performance. He then proceeded to offer a dizzying list of recommendations: study longer hours, earn more money, marry a good spouse, buy a reliable car, watch less television, spend more time browsing the internet for material related to the subject under study, attend more academic workshops and seminars, exercise more frequently, pray more regularly, go to fewer movies, play fewer video games, cut your hair more often, drink more tea or coffee, and so on. Needless to say, such over-specified advice is almost meaningless in practice. The regression model may fit the observed data extremely well, but with many correlated predictors it may suffer from multicollinearity, unstable coefficient estimates, overfitting, and poor out-of-sample performance. The classical understanding of generalization is based on the idea that model complexity must be carefully balanced. In the traditional underparameterized regime, the relationship between model capacity and test error is often represented by a U-shaped curve. If a model class is too simple, it lacks the expressive power to capture the underlying structure of the data, leading to high bias and underfitting. If the model class becomes too flexible, it may begin fitting spurious patterns or noise in the training data, increasing variance and reducing performance on new observations. Conventional wisdom therefore suggests that practitioners should seek a sweet spot that appropriately balances bias and variance. This can be achieved through explicit control of model complexity, such as choosing a smaller model or limiting the number of predictors, as well as through regularization strategies such as lasso shrinkage or early stopping. This philosophy is broadly consistent with Occam's razor. When competing models explain or predict the data comparably well, the simpler model is often preferred because it may be easier to interpret, more stable, and less prone to overfitting. Within this classical framework, the interpolation threshold, the point at which a model has enough flexibility to achieve essentially zero training error, was traditionally viewed as a region of particular risk. Near this threshold, a sufficiently flexible model can fit every training observation, including noise or idiosyncratic features of the sample. In familiar low-dimensional examples, this can produce an erratic or highly variable fitted function that generalizes poorly to new data. For this reason, Traditional model building practice generally favored operating well before the interpolation threshold rather than increasing complexity until the training data were fit perfectly. Accordingly, the dominant textbook picture of model building was the U-shaped risk curve associated with the bias-variance trade-off. Increasing complexity beyond an optimal point was generally expected to increase test error because the model would begin fitting noise rather than signal. This parsimony-oriented tradition encouraged explicit variable screening and restrained model specification in classical statistics. Modern machine learning methods, however, began to offer a different strategy. Rather than requiring a small set of predictors, some algorithms could incorporate very large numbers of variables while controlling prediction error through ensemble methods, regularization, and other algorithmic mechanisms. Stepwise regression is now widely criticized as an unstable approach to model selection when used mechanically. Random forests, introduced by Leo Breiman, represented an important milestone in high-dimensional machine learning by providing an early and striking example that predictive performance need not necessarily deteriorate simply because the number of predictors greatly exceeds the number of observations. A frequently cited illustration comes from the microarray literature, in which random forests were applied to a lymphoma gene expression dataset with roughly 81 cases across 3 classes and 4,682 predictor variables, producing a very low out-of-bag error. Their effectiveness in this regime does not arise from overparameterized interpolation in the modern neural network sense. Instead, random forests reduce variance by combining many decorrelated decision trees, using bootstrap aggregation and randomized feature subsampling as forms of implicit regularization. Although a sample size of 81 observations would not be considered big data by contemporary standards, the example was nevertheless historically significant. Traditional statistical models can become difficult to estimate when the number of predictors greatly exceeds the number of observations because of multicollinearity, overfitting, and unstable parameter estimates. Ensemble-based machine learning methods demonstrated that useful prediction could still be possible in such high-dimensional settings. In this sense, random forests help challenge the simplistic assumption that a large number of variables is necessarily a statistical liability. The more important lesson was not that complexity is always beneficial, but that the consequences of complexity depend heavily on the structure of the model and the mechanisms used to control variance and generalization error. Advances in computing power, large-scale data, and machine learning have made it possible to construct highly complex models that nevertheless achieve excellent predictive performance. Neural networks, for example, possess remarkable representational capacity. The universal approximation theorem establishes that, under appropriate conditions, even a feed-forward neural network with a single sufficiently wide hidden layer can approximate a broad class of continuous functions to arbitrary precision. This theoretical result concerns representational capacity. It does not guarantee that a network can be efficiently trained, will generalize well, or can solve every practical problem. For many complex, high-dimensional prediction tasks, some of the best-performing models, such as deep neural networks and gradient-boosted ensembles, can also be difficult to interpret. This creates an important tension between predictive accuracy and transparency. As one remedy, researchers increasingly use methods such as Shapley additive explanations, to estimate and visualize how individual features contribute to particular model predictions. In applications where interpretability is especially important, practitioners may instead favor simpler and more transparent models, even when doing so entails some loss of predictive accuracy. Nevertheless, The rapid expansion of computational power, the emergence of foundation models, and the availability of large-scale data have prompted a major reconsideration of the long-standing preference for parsimony. Artificial intelligence and data science developed as partly distinct fields, but their boundaries have increasingly overlapped. Modern AI relies heavily on big data and computational infrastructure, while contemporary data science increasingly incorporates machine learning and AI methods for prediction, pattern discovery, and decision support. More importantly, recent work on highly overparameterized models has revealed behavior that does not fit neatly within the traditional U-shaped bias variance story. In some settings, predictive performance can improve again after a model passes the classical interpolation threshold, a phenomenon often described as double descent. This development does not make Occam's razor obsolete, but it does force us to reconsider what simplicity should mean in modern machine learning. Stay tuned for a closer look at how overparameterization, interpolation, and double descent challenge the conventional wisdom of Occam's razor. See you in the next video.